The second session. We have 6 speakers. To the speakers, please try to finish on time. To make sure that you do, I'm going to stand up after 11 minutes. After 12 minutes, I'm going to drag you off the podium. This is so that there is time for discussion during the 15 minutes allotted to you, not outside of it. So the first speaker is Vishwarup Mukherjee from SN Bose.
Okay, thanks everybody, and thanks to the organizers for giving me a chance to speak in this nice meeting. So what I'll be talking about is the work which I have been doing for the past 1 year or so at the SN Bose Center. This is about the microscopic origin of temporal heterogeneities in the translational dynamics of liquid water. Okay, so I'll be attempting to understand this origin of this heterogeneities in the dynamics and how that is actually coupled to the exact rotation mechanism in water. So water is a hydrogen bonded fluid, so in order to rotate, it actually has to break some hydrogen bonds and form some new hydrogen bonds. So this particular mechanism leaves its footprints also on the translational dynamics. So this sort of coupling is very interesting for water, and it is expected that this should be a sort of universal behavior, which is also true for other hydrogen bonded fluids. So what I'm going to talk about is pretty generic features, and this is reported in this work which came out in the JCP last year. Okay, so in terms of simulation details, it is pretty simple simulation. We just simulate a classical MDE of a box of water molecules at several temperatures. So primarily, I'll be concentrating on the dynamics data at 300 Kelvin. So it holds, all these things holds at lower temperatures also. And typical system sizes are about 2000 water molecules. Okay. So if one looks at the full mean square displacement, so this is the translational mean square displacement as a function of time. You have typically these 3 regimes. One is the initial ballistic regime where the mean square displacement scales as t square, and it goes over to in the long time goes over to a scaling of t, and in between there is this caging regime where the exponent is less than 1. So now I'll be actually concentrating in this regime of this band of time scales, and these are the relevant time scales affecting the rotation of water molecules. So I'll be concentrating on these time scales and talking about rotation translation coupling in these time scales. So if one plots this non-Gaussian parameter, which actually quantifies the fluctuations in the dynamics, so that also peaks around this time scales, so that these fluctuations are most significant in around this band of time scales. And with the onset of the diffusive regime, these fluctuations go, and you have this peak and diffusion at long times. Okay, so to start with, let's look at this reorientations in water in a little bit of detail. So this is a very simplest pointer of these reorientations. So you take a box of water molecules and you simulate it, and you just randomly select some water molecule and point its, try to calculate the time series of the angle between one of its OH vectors and one of your directions in the simulation box. And if you look at the time series, you see certain features, that there are some diffusive reorientations, and on top of that you have these sort of very large orientation angular jumps. And these jumps can be as high as around, say, 50 degrees or 60 degrees in a relatively very short time. So this was pointed out in a very seminal paper by Damian Lage and Heinz in 2006. So these reorientations in water in general proceeds by a combination of these large amplitude jumps and diffusive rotation. So this contradicted the traditional Debye picture, which actually said that reorientations happens in small angular steps in small time. So this contradicts that picture. So these orientational jumps are driven by fluctuations in the coordination of hydrogen bonds, and the typical free energy barriers are around 3.5 kT, so they are very accessible at room temperatures. So this is the most important channel by which water reorientation happens. Okay, so how does the manifestations of these jumps? The standard thing is, at least in simulations, is to calculate the reorientation correlation functions. where you look at how much a tagged OH vector rotates in a time interval t. And for liquid water, these things are exponential functions of time. And if you take the long time of these functions, Pn is the Legendre polynomial, and n is the order of that. And suppose you have a completely diffusive reorientation, then you can explicitly analytically show that this tau1, which is related to the time scale of relaxation of C1, and tau2, which is related to the time scale of relaxation of C2, the ratio is 3. So if you actually compute this ratio from MD simulations, it comes out to 2. So that is a pointer that diffusive reorientations are not playing here. The jumps are there. Additional, I mean, from experiments also, these jumps are now in a very firm footing, because only when you actually include these effects of the jumps, the discrepancies between these reorientation times obtained from two different experiments, NMR and quasi-elastic neutron scattering, they disappear, and these reorientation times agree with each other. So that is only when you invoke these angular jumps inside the models which are used to fit with the neutron scattering data. Okay, so how do you identify these orientational jumps? So you take a typical MD trajectory. So what you see, this is the thing what I'm talking about. So this reorientation jump actually is associated with the hydrogen bond partner exchange. So you look at this rotating water, which is marked as O star. It was initially hydrogen bonded with one of these water molecules, OA. So it breaks this hydrogen bond, simultaneously rotates and forms a hydrogen bond with another one. So from the simulations, you try to locate all these discontinuities in the neighbor of these of the rotating water molecule. So this is a schematic of the time series of the neighbor of this rotating water molecule. So at certain time, it is hydrogen bonded with some water molecule A. At a later time, it breaks this bond and forms another hydrogen bond with another water molecule B. So you identify the starting and ending times of these reorientation jump process, and also the identity of the initial and the final partner. So you do these things and then perform a coherent averaging of these trajectories. By coherent averaging, I mean you actually coincide the transition states of all these jumps, and you get a sort of average mean picture which looks like this. So here is the sequence of events in increasing temporal order. So it is this molecule is initially H bonded to this OA, and finally it breaks this bond and it is hydrogen bonded to OB. So what actually happens is if you're tracking these two, I mean one angle and two distances, the angle is formed by this rotating vector and projection of this rotating vector on this plane. So this peculiar way of looking at rotations over here is very important for water, because of these OH vectors are liable to high amount of libration. So here the slow coordinates are the oxygens. So you actually measure everything with respect to the oxygen. So you project this OH vector on this plane and look at the angle, and you simultaneously track these two distances. One is between the rotating vector and the initial hydrogen bonding partner, and the rotating vector and the final hydrogen bonding partner. So if you track these two distances, you see one of this, the initial initial hydrogen bonded partner moves from the first solvation shell to the second, and simultaneously the second one moves, the final partner moves from the second shell to the first one. And this rotation and this coupled translations, all these things actually happen simultaneously. Okay, so from this you can actually sort of have a glimpse of what is to come. So I'll sort of try to define two time scales associated with this rotational process. One is the time of waiting, when the waiting time is defined as when these hydrogen bond exchanges are not happening. And this jump time is defined as the time of flight when this exchange is happening. So as you can see, if you look at even at the translational dynamics, the translational dynamics during this jump time is much more rapid compared to what the dynamics at the waiting times. Okay, so this is a generic feature. This also happens for other hydrogen bonded systems. These are given in other papers. Okay, so these two time scales, there are these two time scales associated with this rotation. One is this waiting time, which comes about to be around 2.6, and another is this jump time, which is the time of flight. So we have already a time scale separation between these two. So the next job is to decompose the translational dynamics during these two periods of waiting and periods of jump. Okay, so what we would be looking at these dynamical quantities, the Van Hoff function, which gives the probability distribution of the displacements, and these angular brackets denotes averaging over time origins and molecules. So when we calculate the partition dynamics, the important thing is to actually choose these time origins in an appropriate manner. So that is schematically given over here. So from the knowledge of these reorientation jumps, for each molecule, you know, so suppose this is a schematic of the time axis. So you know the periods of the jump and periods of the waiting from the analysis of the trajectories. So now you take some interval for calculating your dynamics, and suppose I want to calculate the dynamics during the intervals of waiting. So if this interval actually coincides with my periods of jump, I don't allow. And if this interval falls fully in the waiting time, then I allow. So you can do the similar thing for the jump times. So on doing it, you can very easily see that the dynamics actually separates. The dynamics during jumps is very fast, and dynamics during waiting time is much more slower. So these are shown at two time scales. One is equal to the mean jump time, and this is at 10 times the mean jump time. And this is data at 300 Kelvin. Okay, so now on top of that, if you put in the red curve is the full dynamics. So the red curve is sort of intermediate between the waiting time dynamics and the jump time dynamics. So to get an approximate, very brute force idea of how much this heterogeneity is, I have just fitted these two probability distributions, the Van Hoff functions are arising from the translation during jump and the waiting time, and the ratio of these diffusion coefficients which you extract from this is around 3.8. You have the similar behavior in MSDs also. So this brings me to the conclusion. So this temporal heterogeneities actually arise due to specific nature of the mechanism of orientation. And the translational dynamics is at par with the rotational dynamics. It shows these two time scales. So this is also expected for other hydrogen bonded fluids, and this is something which I'm sort of trying to go to extend this method to find a microscopic measure for rotation translation coupling for hydrogen bonded fluids. Thanks.
Thanks, Bishwarup.
Yeah.
Questions?
Vishwarup, can you go to the last slide? You said something fast. No, the one, yeah. So, I mean, most of what you're presenting was analysis in the caging regime, right? So the diffusion coefficients are extracted how?
These are from the fits of these Gaussian. We try to fit Gaussian. That is not a very good job, I know, but it's a sort of brute force to get some idea because these functions are not strictly Gaussian. They have exponential tails also. So the better job, more sophisticated job would be to fit also the exponential tail. And so that is something I'm trying to do.
Okay.
Yeah. No.
The whole thing.
No, I try to fit the whole.
That the fitting is not.
Yeah, exactly. Yeah.
No? Okay. We go on.
Thanks.